starting with differential equation of SHM. d2x upon dt2 plus omega square x is equal to 0. We can derive expression for acceleration of particle in SHM, velocity of particle performing SHM, and its displacement. In time t. So, from differential equation of SHM, linear SHM, let us try to find out these all physical quantities. And what we know is, so the given particle of mass m performs linear SHM along the path AB, where O is the mean position. And for the given time t, the particle can be at any of the position P, where the particle gets displaced through the distance x from the mean position. And for the given time t, the differential equation is d2x upon dt2 plus omega square x is equal to 0. Therefore, we can write this expression as d2x upon dt2 is equal to minus omega square x. The term omega square x on the left hand side, we have taken it to the right hand side. This is the second order derivative of displacement. Second order derivative of displacement is acceleration. So acceleration is minus omega square x. For the particle performing linear simple harmonic motion. And so let us take this as equation number 1. So we'll record it somewhere over here as acceleration is minus omega square x. Here, acceleration and displacement are in opposite direction to each other, so the negative sign. We also know that omega square is k upon m. Now, what is acceleration? Acceleration is a rate of change of velocity with respect to time. So, dv upon dt is equal to minus omega square x. Here in this case, we can have a little rearrangement. Instead of differentiating velocity v with respect to time, let us differentiate with x. And so this will be dv upon dx. Now as we are differentiating it with respect to dx, but originally it is with respect to t, so this can be written as dx upon dt. Okay. So dv upon dt can be expressed as dv upon dx into dx upon dt. So the original value remains same. So this will be equal to minus omega square x. But what is dx upon dt? It is the rate of change of displacement. A rate of change of displacement with respect to time is velocity. So for dx upon dt we can write v into dv upon dx. This is equal to minus omega square x. Now with the variable separable form, let us take this dx from the left hand side, which is in the denominator. We will take it to the right side, it will go to the numerator. And therefore this becomes v into dv, which is equal to minus omega square x into dx. Now here we come to know that v is with its small increment, that is dv, x is with its small increment dx. Let us integrate it on both sides. Integrating the given expression, integration v dv will be equal to integration minus omega square x dx. Integration v dv can be expressed as v square upon 2. This will be minus omega square is the constant term. So integration x dx can be expressed as x square upon 2 plus say constant of integration c. Now for particle performing simple harmonic motion, we know that as the particle shifts along the path, the value of velocity keeps on changing. And so when the particle reaches the extremity either B or A, the velocity becomes 0. When velocity becomes 0, the displacement becomes maximum, so x is equal to A, which is the amplitude of SHL. And so over here, if we take the constants as, if the value of x is A, then the value of V becomes 0. Therefore, substituting these particular values over here, the left hand side will be 0. This will be equal to minus omega square. The value of x will be A. So this will be A square upon 2 plus C. And so let us take this value minus omega square A square upon 2 on the left hand side. It is going to be a positive term. And so the value of omega square A square upon 2 will be equal to C, which is the constant of integration. As we have integrated the thing, we are able to get the value of C, knowing the value of x and v. And so if we substitute this particular value in the given equation, v square upon 2 is equal to minus omega square x square upon 2 plus c, we will be able to get the expression as, this expression will become v square upon 2, this will be equal to minus omega square x square upon 2 plus omega square a square upon 2. So from both sides we can eliminate the common term, that is 2, and we can take omega square common again, and we can represent this particular expression as v square is equal to omega square in the bracket a square minus x square. And so the value of v is thereafter expressed as plus or minus, because we are taking the root value omega under root a square minus x square. And so here we get the value of, or we get the expression for velocity of particle performing simple harmonic motion along the path AB about the mean position O. Now here we are having plus or minus sign because it will depend upon how the particle is traveling on the path, whether it is moving along the positive x-axis or it is moving along the negative x-axis. This expression for the vertical movement, if the particle moves up and down, this expression can be given in terms of y. Then v will be equal to plus or minus omega root of a square minus y square, plus or minus value. V will be positive if it goes upside and negative if it comes in the downward direction. And so from this expression, now we have another expression with us, that is velocity of particle performing simple harmonic motion v is equal to plus or minus omega under root a square minus x square. Let this be equation number 2. Fine. Now we are having the expression of velocity v. Plus or minus is giving us the direction, whether it is moving along the positive x-axis or whether it is moving along the negative x-axis. Yes, but the magnitude can be taken as v is equal to omega under root a square minus x square. This is the magnitude of the velocity. It depends upon the angular velocity omega, amplitude a, and the position of the particle along the path. We know v is dx upon dt, a rate of change of displacement with respect to time. So this expression can be written as dx upon dt. This is equal to omega under root a square minus x square. Now here dx is on the left hand side and x is on the right hand side. So with the variable separable form again, what we can do is, let us take the terminologies with the x along by dx. So dt will take it on the right hand side. So the expression becomes dx upon under root a square minus x square. This will be equal to omega into dt. Now if you integrate this particular, extremely sorry, this is dx. Yes. Now if you integrate this particular relationship, integration dx upon under root a square minus x square, this will be equal to integration omega dt. Now in this case, if you see this particular integral value, this is nothing but sine inverse of x upon a. See, if we take this particular function sine inverse of x upon a as say y, and if we differentiate this with respect to x, dy by dx, then this will be d of dx of sine inverse of x upon a. Now the formula is 1 upon under root 1 plus square of this value x square upon a square minus multiplied by derivative of x upon a, and so this will become 1 upon under root a square minus x square upon a square. That can be taken as root of a square. It will go as a multiplied by x upon 1 upon a, derivative of x upon a. And so we can say that the derivative of sine inverse of x upon a is 1 upon under root a square minus x square. So integral of dx upon root of x square minus x square, it will be written as sine inverse of x upon a. Therefore, this is sine inverse of x upon a. This will be omega constant term. Integration dt is d plus alpha will take as the constant of integration. Therefore, sine inverse will invert the function. It is going to be x upon a is equal to sine of omega t plus alpha. Let us take this a over here. X will be equal to a sine of omega t plus alpha, and this becomes the expression for this displacement in simple harmonic motion. As we get x as the displacement, A is amplitude omega t plus alpha is phase of SHM. Omega t plus alpha is phase of SHM. Alpha is called initial phase. This alpha is going to decide where the particle is present at the start of the simple harmonic motion. Fine. For example, if we consider a path AB, O is the mean position. If the particle is at mean position, alpha will be 0. If it reaches the extremity over here, alpha will be pi by 2. And so likewise, whatever may be the position of the particle over here, the value of alpha will be decided. If particle is over here, t is equal to 0. It is not at the mean position. So, when the SHM begins from this particular position, this is the initial phase, alpha. And then as the particle moves, this will be omega t. So this will be x, this will be alpha, this will be omega t. So the angle will be omega t plus alpha. So this is called as initial phase, or it is called as epoch of SHM, or epoch of SHM, or it is also called as starting phase. Alpha is called as starting phase. Omega t plus alpha is called as phase of SHM. Yes. And so now we can list up the three important formulas, three important expressions which we have derived from starting with the differential equation of SHM as number 1, acceleration in SHM is minus omega square x, velocity of particle performing simple harmonic motion is plus or minus omega under a square minus x square, and displacement x is equal to a sine of omega t plus alpha. In some of the textbook it will also be given as a sine of omega t plus phi. What denotation we take over here, phi or alpha or theta, is immaterial. What is important is these are the starting phases. These are the initial phases. Omega t plus alpha, omega t plus phi, these are the phases of SHM. We will have minimum and maximum values for all these expressions depending upon the position of particle in simple harmonic motion.